Okay, I think we can get started. So, welcome to the last talk of the afternoon session. So, it's my great pleasure to have with us Fan Yang from the YMSC, Tsinghua, and from BIMSA. So, let's welcome her.
I'm very happy to have this opportunity to present some of my recent works on instrumental variable analysis. Um, and first, what is an instrumental variable? When we are trying to study the causal effect of a treatment D on an outcome Y, such as what's the impact of smoking on lung cancer, okay? People are very worried that there could be some measured and also unmeasured confounders between the relationship of D and Y. Okay, some of the measured confounders, such as your lifestyle, like your diet, whether or not you do exercise a lot, things like that, gender, maybe they're measured and could be controlled. But there are always some unmeasured confounders there that you might worry, okay, I do not have measured them and therefore I cannot fully control for them. And one example is proposed by Ronald Fisher, who almost single-handedly um, established the modern statistics. He proposed that what if, okay, there is a genetic variant, okay, someone who carries this genetic variant um, may be more likely to smoke and also be more likely to get the lung cancer. And therefore, without accounting for this unmeasured confounder, the genetic variation, you won't be able to obtain the valid inference about this impact on why smoking's impact on the lung cancer. The observed association is confounded by this unmeasured confounder. Okay, and you can imagine unmeasured confounder is almost everywhere unless D is randomized. Okay, and do we have some tools that we can address this unmeasured confounder? Well, one popular tool is to use instrumental variable IV, and a typical IV have the following assumptions on it. First, IV has to be associated with the treatment of interest. Second, IV has to have no direct impact on your outcome of interest. So all the impact of the IV Z here on Y has to go through D. And the other assumption is that the IV Z has no correlation with the unmeasured confounder. So the idea is that we use this instrument which extracts the variation in the treatment that is independent of the unmeasured confounder and uses unmeasured confounder free variation in D to analyze the treatment effect of D1. So this is the big picture idea of the instrumental variable. And my research in the past year focused a lot on instrumental variable because unmeasured confounder is everywhere. And today I'm very happy to have this opportunity to present two of my works, recent works on instrumental variable. Both of the papers are under journal review and are on archive. And one is about two-phase treatment with non-compliance, and the other one is about missing data in instrumental variable model. Okay, let's move to the first topic, two-phase treatment with non-compliance, where we're trying to identify the cumulative average treatment effect by utilizing a multi-site IV. And this is a joint work with my collaborators Guang Lei, Xu, and Zheng Yan. Okay, as you might know, many randomized studies, many well-designed randomized studies, they often involve more than one phases. And this is an example where you have two phases of the treatment. At the beginning, okay, phase one, subjects were randomized to either treatment group or to the control group by maybe flip of a coin. Okay, it's purely random. And then there is a later time point where we call it phase 2. And in this design, people hope that at phase 2, okay, the subjects who receive the treatment at phase 1 will receive the treatment again at phase 2. And the subjects who receive the control would receive the control again at phase 2. That's the ideal scenario people expect. This is because we want to avoid fade out. If you think about the treatment effect on something, let's say that the treatment has a benefit on the outcome, we hope to be able to reinforce this benefit by some subsequent work, by taking the treatment again. Okay, so this is a basic idea of multi-phases treatment assignment. And ideally, we hope that subjects receiving treatment will continue to receive the treatment at phase 2, and subjects receiving the control would continue to receive the control, so that the comparison between the sequence of receiving treatment and the sequence of receiving control is easy because of the randomization. If you randomize subjects, right, and the subjects who take the treatment sequence in both time points and the subjects who receive the control at both time points, they are comparable due to randomization, so that I can easily estimate the causal effect of taking a sequence of the treatment versus taking a sequence of the control by just comparing those two groups. That's easy. But in practice, things are always much more complicated. You can imagine, depending on how an individual has fared during the first phase, they may decide to switch to a different group at phase 2. That is, non-compliance to the original treatment assignment may arise at phase 2. Subjects originally receiving the treatment at phase 1, maybe their outcome is not good, and therefore they decide to switch to the control. And for subjects who originally received the control, maybe they decide that I want to try the treatment, so that they switch to the treatment group. And always it is a case that there's some reason, right, why people want to switch. The switch is not random. There is some reason for that. And therefore, if now you compare the subjects who always take the treatment, no matter phase 1 or phase 2, with subjects who always take the control, right, stick to the control, no matter under phase 1 or phase 2, those two groups of subjects will no longer be comparable. And the causal effect estimation will be challenging. So this is the basic idea. Okay, what we are interested in this type of study is the cumulative average treatment effect. How does the outcome compare had the subjects taking treatment at both phases versus subjects taking control at both phases? Okay, let's use Z to denote the initial treatment assignment, which occurs at phase 1, and we use 0 to denote control and 1 to denote treatment. And let's use D to denote the treatment received at phase 2. Continue to use 1 to denote treatment and 0 to denote the control. And we use potential outcomes framework to define the causal effect. We use this Y11 to describe the outcome had a subject receives the treatment at both phases. And we use Y00 to denote what would happen on the outcome had the subject receive the control at both phases. And the causal effect that we want to obtain is basically a comparison between Y11 and Y00. And here I is the index for subject. For each subject I, this defines the individual causal effect. What would happen, right? What's the impact of taking sequence of treatment compared to taking a sequence of control for subject I? But as we know, for one subject, right? You only take either the treatment or the control. So those two potential outcomes can never be jointly observed for each subject. Okay, so individual causal effect cannot be estimated unless you make very, very strong assumptions. So what people are interested in is always an average difference between y11 and y00. Okay, and this is a cumulative ATE that we're interested in. And in many studies, it could be multi-site. And in multi-site randomized trial, what people did is that within each site, you conduct a study like this. Okay, and for example, you may have many, many hospitals where you can conduct the experiment within each of the hospital, and you may have a lot of schools where within each school you can conduct this randomized trial. And when you have multi-site randomized trial, since it's just a little bit more complicated, but later you will see that multi-site plays a very key role in identification of the causal effect in this setup. Here, let's use Si equals K to denote that subject I site membership is K. Okay, basically, the first expectation is taken over the distribution of subject I in site K. So this is site K specific average treatment effect. And in the multi-site study, we're interested in on average how the treatment sequence does across sites. So you further take expectation, and this expectation is taken over the population of sites. Okay, so this is our focus in this talk. Okay, here's our motivating example, Project STAR. Here, STAR stands for Student Teacher Achievement Ratio. Okay, this is a project launched in Tennessee State, where people are interested in the evaluation of multi-year accumulative impacts of class size on students' achievement. And this is a multi-site randomized trial involving 79 schools. And in each of the school, you conducted this randomization. And in each of the school, students were randomized to either a small class, okay, we denote as z equals 1, or randomized to a regular class, we denote as z equals 0 at the kindergarten year. Okay, and the small class, they have about 12 to 17 students. And for the regular class, the class size is like 22 to 25. Okay, and people are interested in the ATE of experiencing 2 years of class reduction on students' test score at the end of the first grade. And ideally, we hope, right, that for students who were originally assigned to the small class in the kindergarten year, they continue to stay in the small class in the first grade. And similarly, for students assigned to the regular class at the kindergarten year. But as we know, there are many, many reasons that students might want to switch, such as their parents' perception on class size, such as students' behavior, performance, academic performance, things like that. They may cause students to switch to a different class type in the first grade. Okay, and although originally we have randomization, but again, students sticking to the small class all the time will no longer be comparable to students who stick to the regular class all the time. Okay, and okay, now this table shows the non-compliance data after the phase 1. You can see that among those who were originally assigned to a regular class, 248 decided to switch to a small class. And among those who were originally assigned to the small class, 108 of them decided to switch to the regular class. Okay, so here the non-compliance rate in each of the treatment group is about 8%. Why do people decide to switch? There could be many reasons. Some of the reasons might be measured, and some of the reasons may not be measured. And what we found is that, well, perhaps one of the reasons is their academic performance at the end of the kindergarten year. You can imagine for subjects who do not perform well in their class in the kindergarten year, they may decide to try a different class, right? You may decide, I want to switch. I want to see whether the other type of class may fit me better, may increase my academic performance, and therefore they switch. Okay, and here this K-rate math describes the test score combining rating and at the end of the kindergarten year, and this G1 rate math is a score, test score at the end of the grade 1, and this is outcome of interest. And you can see that among those who were originally assigned to the regular class, right? Those who decide to stay have slightly higher test score on average compared to those who want to switch, compared to those who switch. Okay, and similarly, for those who were originally assigned to the small size class, those who stay, on average, enjoy higher test score compared to those who switch. Okay, which means that this kindergarten year test score measured at the end of the kindergarten year may have an impact on the treatment, that they would receive in grade 1. Okay, it has an impact on that. And also you can imagine that how well they did in kindergarten may also predict how well they would do, right, in the grade 1. And therefore, this is a variable that may have an impact on D and have an impact on Y. And also, the class size may have an impact on this variable. On average, the students who were assigned to the small class, they are associated with higher score at the end of the kindergarten year. Okay, so this is a variable affected by Z and also potentially affected D and Y. And this type of variable, we call it post-treatment confounder. Post-treatment is regarding Z, it's after Z, it's potentially affected by Z. And the confounder is confounding the relationship between D and Y. Okay, this is the idea. Okay, now here are our methodological challenges to deal with uh, the causal effect estimation. First, as we said, people switch for some reasons, right? And it may be good measured, or it may be some are measured or not. So you may have confounders between the dy relationship, and some of them are measured, we denote as x, and some of the reasons are not measured, we denote as u. U is unmeasured. And because we're interested in the effects of a sequence of treatment, essentially, and the standard strategy in causal inference to estimate the effects of a sequence of treatment is what we call IPTW, the inverse probability of treatment weighting. However, IPTW has some very strong assumption underlying it. The assumption is strong ignorability, means that both Z and D are conditionally independent or are kind of randomized given observed covariance X. But here, have U. So only conditioning on X, D is still not randomized. Okay? but IPTW cannot address U, the existence of U. So this method will fail when you have U between the dy relationship. So this does not work. How to address the unmeasured confounder U? As we said, we often use instrumental variable. So does the instrumental variable, the standard instrumental variable strategy work? Well, it doesn't. It can address the problem caused by U. But in our study, we are very concerned that Z may have a direct impact on Y. That is not through D. You can imagine perhaps students who were in the small class size, they received more attention from the teachers, right? And perhaps they have better study habits. And this better study habits may have an impact on Y. That is not through D, right? So it's so it's just too strong if we assume that Z has no direct impact on Y. And also, you can imagine that there could be Z by D interaction. The benefit of taking a small class may be amplified by by being in the small class again. So we suspect that there could be direct impact of Z on Y, and also there could be interaction between Z and D, which makes a key assumption for the instrumental variable not valid. That's what people call exclusion restriction. Exclusion restriction is the assumption which says that there is no direct effect of Z on Y. That is not through D. It's apparently we shouldn't assume this very strong assumption. Okay, so the standard IV method does not work. Further, as we said, how the students perform at the or the test score at the end of the kindergarten year, we denote as V. It may predict both D and Y, right? And also it's affected by Z potentially. And given the existence of this variable, again, it opens the door between Z and Y that is now through D. So again, the existence of this post-treatment confounder will also violate the key assumption of the standard IV method. Okay, so there are a lot of methodological challenges that we hope to address. And essentially, this is the causal structure that we suspect or we think may be plausible, at least compared to the other assumptions. That is, there could be direct effect of Z on Y, and also there could be direct effect of Z on Y through post-treatment confounder, which has an impact on D. Also, there could be measured and unmeasured confounders between the VDY relationship. So this is a causal structure that we would like to recover. But as we mentioned, neither IPTW, the weighting or standard IV method would be adequate for this setup. Okay, now here is what we have in the literature by utilizing multi-site instrumental variable. This is multi-site multiple mediator instrumental variable strategy. And this is a causal graph underlying their method. If you compare this with our with what we want, you could see that it's much less complicated compared to what we want, right? First, what they are interested in is those two impacts, the impact of D on Y and the impacts of V on Y. But notice that in their graph compared to ours, they cannot allow V to have an impact on D. They are parallel. They're conditionally independent given Z, X, and U. And also, you realize that, well, there is no direct impact of Z on Y, which we think we shouldn't simply ignore. Okay, so but this is the basic setup where this motivates us to build our work upon their strategy. And what they did is that, well, given this causal structure, they conducted the following analysis. They first do a side-by-side ordinary least squares analysis to calculate within each site, in each site K, what's the average impact of Z on V, average impact of Z on D, and average impact of Z on Y. Then, after you estimate those three impacts, okay, within each site, you plug them in into a site level OLS analysis. You regress the Z's impact on Y, on Z's impact on D, and Z's impact on V. And then gamma 1, gamma 2 recovers what you want under, of course, some assumptions. Okay? But I would say that their framework does not formulate the underlying causal assumptions in a very clear way. And we hope to make things more transparent. But as we said, it does not have the cumulative ATE as estimate. It's not what we want. And also, it requires the exclusion restriction. So they eliminate the possibility that there could be a direct impact of Z on Y or an interaction between Z and D. And also, they require that D and V to be parallel mediators that are conditionally independent. But what we want is that we want to allow for direct effect of Z on Y. And we want to allow for possible interaction between Z and D on Y. And also want to adjust for this post-treatment confounder V, as well as measured and unmeasured confounder in the dy relationship. Okay, so this causal structure is our goal. Okay, now here is our theoretical model. Basically, we explore under what conditions you will be able to recover what you want. Okay, and this is our theoretical model for the potential outcomes of V dy as a function of Z. And let's take a look at the first one, VIZ. This describes the kindergarten, what the kindergarten test score would be had the students been assigned to class type Z. Okay, and we assume that it's linear in Z, but Z is binary. And you could see that in those coefficients, it's individual specific. We have the intercept indexed by I, and here we have slope on Z indexed by I, which means that we allow those effects, okay, or intercepts and the slopes to be a function of the subject's characteristics and the site characteristics. Essentially, they can be functions of X and Y. Different subjects can have different impacts of C on their V. We allow this heterogeneity, essentially. And then for D, we model it as a function of not only XU, but also Z and V. And here, our D is binary. So we just follow the social science literature to utilize a linear model for the probability of dz equals 1. We model it linear in Z and V. And you could see that those two parameters, they have I and K there. They can be functions of X and U. And for this parameter, we need to have some restriction. Essentially, we assume that in each of the school K, the effect is constant. But this constant can be different in the treatment group and in the control group. So essentially, what we allow interaction between Z and V, but we cannot allow the impacts to vary across subjects in each of the school in each of the treatment group. That's a restriction that we have to impose, and we haven't figured out a way to make it more flexible. So this one is not individual specific. We will have constant impact here assumed. also you could see that here, if you think about the model for D1, okay, the potential treatment had the subject being assigned to a small class size. This one is just a function of V1, but not a function of V0. So essentially, we also impose that the potential outcomes in the other world, okay, V0, has no impact on what's happening in the current world after conditioning on the current world's V. Okay, so I think it's pretty reasonable. Okay, this is a model for DZ, and also for Y, it's affected by Z and D and V, and also X and U. X and U are embedded in this intercept in this index I here, in those coefficients. Okay, but again, for V's impact, we have to assume that it's constant. And also here we assume that there is no interaction between Z and VV. That's how much we can allow in our model. But notice that we have interaction between Z and D here. Okay. So this is our theoretical models. And under this theoretical models, we can calculate what is our targets, what is our estimate, the cumulative average treatment effect. And what do we do? What we do is that, well, once you have the model, right? You have the model for everything, and you can plug in. Okay, plug into the formula, and then we obtain that under some assumptions, the ATE is represented by the following parameters: gamma 1 plus gamma 2 plus gamma 3 theta v times alpha 1. What are they? Alphas, they are parameters in the V model. Betas, they are parameters for the D model. And gammas, they are parameters for the Y model. And also theta v, they're parameters for the Y model. And here, when we drop the index I, for example, this gamma 1k, it means that it's an average of gamma 1ik after taking the average over subjects I inside. Okay, and if we further drop k, it means that we further average gamma 1k over psi. Okay, so this is essentially the average of the parameter z here. Okay, and plus the average of gamma 2, plus the average of gamma 3, then plus the average of V's impact on Y times the impact, the average impact of C on V. Essentially, this is those three, 1, 2, 3, and 4. Essentially, that's those pathways. Okay. But we have to impose some assumption. You can see here, when you want to drop this k, right, and the trait, the expectation of the product of the expectation, you have to assume no correlation. Okay, or you can put down a stronger assumption, they're independent, which means that this pathway, okay, this impact across schools has to be independent of V's impact on Y. Is it always plausible? Of course, it's not always plausible. It's an assumption that potentially could be violated. This assumption essentially says that for schools that have higher impacts of class size on their first grade, on their kindergarten test score, it would be violated if schools that have let's see, higher impact of class size on the kindergarten test score, if it's associated also with a higher impact of the of the kindergarten test score on first grade test score, then you could see that this must be violated, right? So there could be potentially violation. And what can we do if there is violation? Well, a way to go is to use some sensitivity analysis. What if there is such amount of association, which we don't know? You have to plug in a value. Then how much impact will there be on ADE? But that's some subsequent analysis. But for now, let's assume that you have those two effects being independent across schools. Okay, if you think about the problem, previously we have models which are theoretical models underlying the data structure and generate the data, and they are models for potential outcomes. But you can imagine, for example, this VZ. Everyone has two VZ. One is V1, one is V0, right? But in reality, subject is either assigned to small class or assigned to regular class. You can only observe one of these two. So you cannot directly work on this model. You have to link this model to observe the V instead of the potential outcome of V. And this is what this reduced form model is doing. But the link is simple. You can imagine, for subjects who were assigned to a small class, you observe V1, right? And for subjects who are assigned to a regular class, you observe the V0, okay? And given this relationship between the observed V and the potential outcome V, you can plug in the models for V0 and V1 and obtain the results between the relationship of V, observed V and Z. But another thing that you realize that, well, originally you have alpha 0 ik, right? But now you put in the average there. What's the difference? Well, we put in the difference between alpha 0 ik and alpha 0k into the residual. And similarly for this term, you put the difference between alpha 1 ik minus alpha 1k times zik into the residual. And you would see that due to randomization of Z is independent of those individual specific alphas, and therefore this residual is uncorrelated with Z. So you can unbiasedly estimate alpha. Okay, so this is the idea. And similarly, you do the analysis for D and for Y, and the alpha 1K, beta 1K, theta 1K is a site level causal effect of Z on V, D, Y respectively. And what is theta 1K? You realize, okay, there are some relationships among those parameters. Theta 1K equals gamma 1K plus gamma 2K times beta 1K plus gamma 3K times beta 2K. Here, beta 2K is a sum of beta 0K and beta 1K. And then plus theta VK times alpha 1K. We have a lot of the parameters that we're interested in, right? We're interested in gamma 1 aggregating over K. We're interested in gamma 2, gamma 3, theta V, alpha 1. If we can analyze those parameters, we obtain our results. But those are set level instead of the average of gamma, right? So what can we do? Well, again, just like what we did here, we absorb the difference between gamma 1K and gamma 1 into the residual. And you could see that this is equivalent. This is equivalent by writing, by adding an epsilon K here, okay? And, but in this process, in order to have the residual to be uncorrelated with those predictors, okay, you have to impose some assumptions. Here, for this result to hold, you have to impose some within site zero covariance assumptions. So those are the parameters in the V model and the D model. Those are some impacts of D on Y in the outcome model. You have to assume that they are those parameters are each uncorrelated with those gamma parameters. And similarly, in order for this epsilon k to be uncorrelated with your predictors here, you can conduct an OLS in an unbiased way, then you have to impose some extra assumptions. And here we need to impose that beta 1k, beta 2k, alpha 1k, again, parameters in the V and D model. Those impacts have to be independent of the Z and D's impacts on Y and the V's impact on Y. So those are some behavioral type of assumptions that is utilized a lot in social science and in economics. Okay, so as you can see, we also have to impose some assumptions in addition on top of the theoretical models. We have to assume that Z is randomized in each site. So we have within site ignorable phase one treatment assignment. So basically, we have to utilize the randomization in Z. It's independent of X, it's independent of U, in order to make the analysis valid. And also we impose some within site zero covariance assumption and some between site independence assumption. And those assumptions are sufficient for us to identify what we want. Okay, now given the above description and idea, the analysis is simple. So basically what we did is the following. Within each school, we estimate the causal effect of Z on Y, Z on V, Z on D, and Z on Y. And we can get those what people call ITT effects, alpha 1k hat, beta 1k hat, and theta 1k hat. And then we plug into a second stage analysis, that is a site level OLS analysis. We regress the estimated effects of Z on Y on those estimates obtained from the first stage. And then you can obtain estimates of gamma 1, gamma 2, gamma 3, those parameters, and theta v. And then you just plug into the formula for the cumulative ATE, you can get your estimate. Okay? But one thing to notice is that those predictors are estimated. There is estimation error, right? Estimation uncertainty in that. But if you have sample size within site increase, the measurement error would reduce. So the estimates are still consistent, but due to that, those predictors are estimated with some uncertainty. You have you have finite sample bias. Okay, that part cannot be avoided. And for inference, we just conduct a multi-level bootstrap because it's a multi-level data. Subjects are clustered within site. So what we basically does is that you do a bootstrap at the site level, and within each site you further conduct bootstraps. That's the idea, the multi-site bootstrap, because the inference, directly obtaining the asymptotic variance of our estimator is very challenging. So we resort to bootstrap. But the analysis doesn't take much time, so bootstrap is okay. Okay, now here are some simulation results. Basically, we try different number of sites, 25 small sites, a small number for sites, 100 a slightly bigger number of sites. And also for each of the K, we also take a look at how our estimator perform with different numbers of subjects in each site. We try 30 up to 5,000. And we compared five is essentially 5 different methods. One is a naive. Naive compares, because what we want to estimate is the treatment effect had subjects taking a sequence of the treatment versus taking a sequence of control, right? So here, this naive means that we just take a look at the results for the subjects who take a sequence of treatment and compare that with the results for the subjects who take a sequence of control. But as you imagine, there is noncompliance, which causes that those two groups are not comparable, right? So this naive methods cannot address that part. And this naive adjust means that we further adjust for observed covariance X in the analysis. This IPTW is a weighting. As we said, it cannot address the unmeasured confounder issue. And MS2T IV is our proposed method. And also, we propose a better method, which allows you to account for covariance X. So essentially, we suggest putting down the centered X and also action with Z into your first stage OLS. That is, you further include the centered X within site and also the centered X times Z as your predictor in those models in order to account for some observed covariance because they are there, right? By accounting for them, your analysis may improve the estimation efficiency in those parameters. And if you can improve the estimation efficiency in those parameters, you also reduce the measurement error in your predictors. And therefore, you can improve the finite sample size. That's the idea. And also, by controlling for observed X, it may make this within site zero covariance assumption more plausible. Then what you need is that given this covariance, okay, you have the zero covariance assumption conditional on this observed covariance. It makes this assumption much more plausible. Okay. Now, if you take a look at the bias first, you realize that for our method, okay, you could see that as sample size increase or as k increase, our methods to have smaller and smaller, right? Tends to have smaller and smaller bias. However, the bias still stay no matter how big your k or k is for the other three methods because they cannot address a measured confounder issue. In terms of efficiency, this is the part that our method doesn't do a good job. Our method have larger variance compared to the other three. Why is it the case? If you think about the second stage analysis, right? It's conducted at the site level. So the number of sites essentially gives you the number of observations. If you don't have a large number for the sites, then you essentially don't have many observations. And of course, the estimation of those parameters won't be very efficient. So this is what causes large variance, but the variance will decrease as sample size increase. And if you compare MSE as a sample size increase, we enjoy smaller and smaller, right? MSE but for the other methods, because they have very large bias and the bias stay no matter how you increase the number of NK and K, so those values they do not diminish as K or NK increase. So this is what we observe. So basically, our method will work well, address both the bias and the variance issue, efficiency issue, if you have a large number of sites and also have a large number of samples in each site. Okay. All right. Now we apply our strategy to the project star, and we found a point estimate of the cumulative ATE as 21. So on average, students who take the small class all the way, they enjoy higher academic performance compared to students who stay in the who takes a regular class all the time. And the inference for the bootstraps, the 90% confidence interval does not include zeros, so this effect is significant. Okay, so small size for the class size is helpful to improve subjects' academic performance. Okay, a brief summary for this part. Um, we provide a consistent estimator essentially for the cumulative ATE, and we investigated when it will work or when the performance will be very good. And also compared to the IPTW, we can address the measure confounder issue. Compared to the standard IV analysis, we can address the exclusion restriction issue. So it is this part. And 5 more minutes. Okay, so I will briefly talk about what I did for the for the missing data. So as we know, in whatever analysis, right? When you propose a model, you hope everything is measured so that you can analyze it. But unfortunately, in practice, missing data happens a lot. It's like a rule rather than exception. And in my this work, what I'm trying to address is the missing data in the treatment and in the outcome when you have missing not at random. What does missing not at random mean? Well, people characterize the types of missing data into three groups. One is missing completely at random, meaning that why the data is missing have nothing to do with anything. You can imagine this is simple, right? Because in such a case, if there is no particular reason for something is missing, then subjects who have complete observations of everything, they're comparable to subjects who have missing data. And therefore, you just analyze subjects who do not have missing data, then your job is done, right? It's very simple. And the other type of missingness is called missing at random, meaning that um, there is some reason for the missingness. However, this reason can be accounted for. The missingness, the chance of missingness only depends on observed data, but not unobserved data. So you can imagine this is also simple because you know the observed data, right? So you can account for this type of missingness. But what is challenging is when you have missing not at missing not at random means that the missingness does not only depends on values that are observed, but also depends on values that are unobserved. In such a case, there could be identification issue. You may not be even able to identify what you need in the model. And in general, identifiability or identification cannot be achieved without further assumptions. What I did in this paper is that I try to explore, because there could be many key variables that are missing, such as the treatment and outcome. For example, let's say outcome is income. Okay, perhaps subjects with with higher income, they may be less likely willing to report. Okay, so Y may have a direct impact on why is missing, right? So the unobserved value has an impact on the probability that it's missing. So that causes missing not at random. And further, this is much more complicated than a standard problem, because under the IV setup, you have this unmatched confounder U. You can imagine unmatched confounder U may also have an impact on whether or not people decide to report. Okay, and therefore there are more than one source of non-ignorable or not at random. One comes from the variable itself, the other comes from this U. Okay, and what we did is that for the a standard or classical setup where Z is binary, D is binary, under what missing node at random conditions you can still identify the causal effect of D on Y. And essentially we did an exhaustive search. And let me show you one example. um, for example, here, let's say that we only consider Y is missing, and this Ry denotes the response indicator for Y. And we figure out, well, you can never allow 3 variables among Z, D, Y, U to affect Ry. At most, you can allow 2, so that you can get identification of this impact on Y. But here you can see that if we choose 2, right, out of 4, we should have 6 combinations. But there is one combination, I think that's ZU affecting RY. This is a very hard, challenging case that you still cannot allow identification under whatever assumption. Well, without a very strong assumptions. So basically, what we did is an exhaustive search of and what um, conditions, right? You can allow identification of the impact of D on Y. Similarly, we conducted an exhaustive search for the missingness in D, and we figure out, okay, those are the 6 setups where we allow identification. And further, we extend the results to scenarios where both, um, both D and Y are missing. So this is basically what we did in this paper. If you're interested, you can search it on archive. Okay, yeah, thank you. It's all about my talk.
Questions, please. Any questions, please? Okay, if there are no questions, okay, if there are no questions, let's thank our speaker again. Thank you.